Thank you. So let me tell you a little bit about remote process control and the protocol for communication that makes that possible for applications in advanced manufacturing and more. We want to rely on great apps that themselves rely on great internet communication. We want voice and video calls that are high definition, high fidelity, high availability, and perform flawlessly. We want to reach out from where we are and manufacture advanced parts anywhere, anytime. We want to control the means of advanced production and connect manufacturers in innovative supply chains. We want applications that communicate life-critical information, vital signs, and vital treatment directives while we're on the way to the hospital. And when we arrive, we want expert consultation and mentoring available to the local healthcare providers, and if needed, telerobotic surgery, bringing healthcare expertise to the front line. To achieve that, we need internet communication that is reliable, assured, and real time. And today's internet communication is none of these. Internet communication behaves this way because it's a single-lane highway. Each packet follows a single path. If any link is congested or fails, delivery of that packet is affected. Apps that depend on receiving all packets in a timely manner will fail or will be considered too risky. This is not only a problem for apps of the future. We have stormy weather today. A study for Bing showed that a mere 500 millisecond delay in search reduced revenue per user by 1.2%. We're talking some real money. A Google study showed that after they deliberately inserted 400 milliseconds of delay, searching after 4 to 6 weeks was down 0.74%. And interestingly, after the delay was removed for those users, 4 to 6 weeks later, search was still depressed. Not so lucky. So one answer really here is US Ignite. Gigabit broadband, but also software-defined networking. My team is using software-defined networking to create and manage multiple paths. We begin here with this diagram, two end systems that are going to communicate. With software-defined networking, we create two redundancy controllers for each, labeled RC. And then these systems and their redundancy controllers communicate through the internet. We have perhaps two apps, to put it in today's terms, as those end systems. And one of the apps now has a packet that's, well, look, it's ready to go. And so the redundancy controller is going to replicate that packet and send it by the two paths that you see here, one green, one blue. And so the redundancy controller gets ready to do that, launches the two copies, and they're received at the receiving end. And they're labeled, say, packet A and B for that particular instance, and the receiving redundancy controller knows that both packets made it through and knows something about the performance of the green and blue paths right now. Now, suppose, after we deliver that packet, on the next packet, perhaps, we have a problem with one of the links in the blue path. You see now with the dashed red line. Congestion or a backhoe have come into our lives. So now, when the sender replicates the packets, only one is received on a timely basis. And the receiver has that kind of immediate information about what's going on in the network and can think about, and the protocol, depending on this, can then say to the sender, perhaps, we have a problem, Houston. Let's build a third purple path along the bottom edge. And now, when the next packet comes along, we again have two functioning paths, and we're back to a fault-tolerant condition, and we never lost anything. We never delayed anything. Our apps are happy. And now it's been getting exciting. Doug Comer has built and demonstrated this as a first step in his lab at Purdue University. With our partners in this project at Kettering University, today we were demonstrating and have been working with the Genie program to build redundant paths via software-defined networking in Genie and put them across the country. And then We demonstrated 3D printing in San Leandro, California today, connecting an application in advanced manufacturing, thanks to Ernest Howland here for his printers in the Omnom project. We monitored that project with the gigabit, 100 frame a second high-definition video cameras from Phase Space and Judi Clark of Lit San Leandro and their 10 gigabit metropolitan fiber network helped make it all happen for us. So these are the members of our team from across the country, university partners, industry partners, gigabit cities. So I want to say thank you now for what we've been able to accomplish so far to US Ignite. The Mozilla Ignite Challenge was the catalyst that caused me to act in the brainstorming round, to form the team, to join these partners and demonstrate as we did today. Thank you to the National Science Foundation and the Genie platform. Their support for experiments in software-defined networking is amazing. I hope that some of the apps that we've seen today will soon be trying to test this service and how it might benefit them. I look forward to deploying it on Manufacturing Hub at Purdue University for small to medium-sized manufacturers across our country. And in summary, we can achieve reliable, assured real-time internet communication if we send multiple copies over different paths, learn which paths to use, build new paths as needed, and deliver a fundamentally new internet service. Thank you very much.